to use the factoring flowchart, you start at the top here. And your first question, whenever you're asked to factor any type of polynomial, is, are there any common factors? If yes, then factor them out and ask yourself again, because sometimes we don't get the greatest common factors, so you want to keep factoring until you've got all of the common factors factored out. Then when you answer no to that question, you can move on. So then the next question you ask yourself is, how many terms does the polynomial have? The first type of polynomials we worked with had 4 terms, and we factored by the grouping method. Then the next type of polynomials we worked with had 3 terms. So if your polynomial has 3 terms, then you can use the factoring box that I showed you or any other trinomial factoring method. But you do want to check to see if your first and your last terms are perfect squares, because if they are, it's possible you have a perfect square trinomial. So that means that both of your binomial factors will be exactly the same, right? But if that doesn't work, or if they're not perfect squares, that's fine. You still want to check to see if you can factor the trinomial into 2 binomial factors. Then, if you're working with a binomial instead, 2 terms, you want to first ask yourself if those 2 terms are a sum or a difference. And here's the reason why. If you have a sum, then you can only factor the sum of a binomial if the 2 terms are perfect cubes. Then you can use the boxes and SOAP that I told you, or you could just use this formula here. But if you're working with squares and they have the same sign, then that's a prime polynomial. Or if, one's a cube, one's a square, it doesn't work out, that they're both perfect, same type, then that's a prime polynomial. If your 2 terms are different signs, then you want to see if you have a difference of 2 perfect squares, then you can just take the sum and difference. If not, you want to see if you have got a difference of 2 perfect cubes, because then you can use the SOAP and boxes. Otherwise, you're working with a prime polynomial. So this flow chart helps you kind of process the factoring of polynomials in your head. So you can ask yourself this, and it'll walk you through how to decide the best way to factor. So let's use that flowchart to factor some polynomials here. Our first example, we've got a trinomial and 1, 2, 3. There's no common factors here, so we're going to try and factor this trinomial with factors of the first term and the last term such that the sum of the products is the middle term. So x squared can only be x times x, and y squared can only be y times y. They do have the same sign. They're both negative. So this actually is a perfect square trinomial. That's x minus y factored twice. Our second example, is there a common factor for all of the terms? No. There's 3 terms, so we're looking for factors of the first term and the last term such that the sum of the products of those is the middle term. So x squared can only be x times x. 12 can be 12 times 1, 6 times 2, 3 times 4. If I want to get 7, I think I might work with 3 times 4. Same sign, both positive. So positive 3x, positive 4x, that works. That means we have factors of x plus 3 and x plus 4. Number 3, do we have a common factor for all of the terms? Nope. So then this is 4 terms. We're going to factor by the grouping method. Let's see what the first group has in common, an x. So let's factor that out. That'll be y squared minus 4. And plus sign, the second pair has 3 in common, so we'll factor that out and divide. Now we have 2 terms, and there is a common binomial factor of y squared minus 4, so I'm going to factor that out and see what remains. But this term, or this factor here, is a difference of 2 perfect squares, so that can factor to the sum and difference of what's being squared, y and 2. and that other factor of x plus 3 completes the factorization for that polynomial. Number 4, is there a common factor for both of these terms? Yes, that'll be 2n. So let me factor out a 2n from those terms, divide to see what remains, 2n minus 3. And I can't factor that any further. For number 5, is there a common factor for all of the terms? No. Let me rearrange these terms because they're not in the proper order. And then I'm working with a trinomial, so factors of the first term and the last term such that the sum is the middle term. So x to the 4th can only be x squared times x squared. And 36 can be 36 times 1, 6 times 6, 9 times 4. It might be 9 times 4 to get 13. Let's see. Same sign, both negative, so negative 9x squared and negative 4x squared. That works. So we have factors of x squared minus 4 and x squared minus 9. But if you go through the flow chart, both of these can be factored further. They're both a difference of two perfect squares. So for the first factor, that's x squared and 2 squared. And for the second factor, that's x squared and 3 squared. So, whew. Those are the factors for that polynomial. Number 6, is there a common factor for these? No, there isn't. Are these perfect squares? No. Perfect cubes? Yes. 4x cubed and 3 cubed. So, cubes use the SOAP and boxes. The first term is 4x and 3. If I want to find, factor, the second factor here, that's going to be 3 of each of these. Box them up. So the first term, that's 16x squared. Middle is 12x, and last is 9. Put the SOAP in. Same, opposite, always positive. For number 7, is there a common factor? Well, yeah, there's a special GCF of negative 1, so I have to factor out that negative 1 from all those terms. It's just going to change the signs, so that'll be positive and that'll be negative. Now I can see if I can factor this trinomial here, so factors of x squared and minus 30, and that's going to add up to positive x. So factors of 30, 30 times 1, 5 times 6 might work because we need to get a 1. Let's see. They're different signs. The bigger number is positive, so that'll work. GCF out front, an x minus 5 and an x plus 6. For number 8, is there a common factor for these terms? Yes, there is 4, so let's factor out a 4 from these two terms. That'll be t squared plus 9. And then look at this binomial. It's a sum, and these are not cubes, so that is prime, which means I can't factor this any further. For number 9, is there a common factor for all of the terms? Nope. It's a trinomial, so let's see if we can find factors of the first and last term that add up to the middle term here. And the first and last term are perfect squares. Let's see if this is a perfect square trinomial. So the square roots here, same sign, both negative. Multiply across, and that actually does add up. So this is a perfect square trinomial. 4a minus 7b factored twice. For number 10, is there a common factor for those terms? No. There's two terms. Are they perfect squares? Sum or difference. It's a difference. So are they squares? No, but they could be cubes. Let's see. That's 5x and 2y. Yep. So we will have two factors here. The first factor is what's being cubed. Then to find the second factor, I need to get 3 of each of these and then box them up by 2. So the first term will be 25x squared, the middle term will be 10xy, and the last will be 4y squared. Same sign, opposite, always positive. For number 11, is there a common factor? And there is x. Oh, what about the number 2 or 4? Yep, 4. So we want to factor out the 4x from this trinomial and see what remains. That'll be x squared plus 5x minus 14. And then we want to see if we can factor that trinomial further. So factors of the first and last term, that's going to add up to the middle term here. X squared's got to be x times x. 14 could be 14 times 1 or 7 times 2. Maybe 7 times 2 because of this. Sum is 5. So different signs, bigger numbers positive. Yep. So we will have an x plus 7 factor and an x minus 2 with the GCF out front. For number 12, is there a common factor for these terms? No. There's a difference, and those could be perfect squares. Let's see. That could be 2a. Yep, those are perfect squares. So we will have a sum and difference of what's being squared, 2a and b. Then 13 says the sum of two squares usually does not factor, right? If you've got like x squared plus 4. Sum of two squares does not factor. That's prime. So is this sum of two squares factorable? Well, do they have a common factor? They do. 9, and that's it. So if we factor out a 9, divide to see what remains, then these are factors. So this is factorable. We would not say this is a prime polynomial.